Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 13, Periodic Motion, Video 8. Today's topics are damped oscillations, forced oscillations, and resonance. The objectives are: know the factors determine how rapidly an oscillation dies out. Understand how a driving force applied to an oscillator at the right frequency can cause a very large response or resonance. Damped oscillations. When a deceptive force is added to an oscillator, the amplitude decreases, and the motion is called a damped oscillation. The simplest case is when force Fx equals negative bvx proportional to the velocity is added to a simple harmonic oscillator. In that case, F net equals negative kx minus bvx. Amplitude and angular frequency for damped oscillation. In the simplest case, when F net equals negative kx minus bvx. In this case, max equals negative kx minus bvx. Ax is double derivative of displacement over time. Vx is just derivative of displacement over time. The equation for oscillation for damping force is when the damping force is small, x equals to a times e to the negative b over 2mt times cosine omega prime t plus phi. So in this equation, you can see the amplitude decreases. So is omega prime actually becomes smaller as well than in the case of no damping. So the factor that affects damping is the value of b. There is critical damping and overdamping. This is the case when the system no longer oscillates, but returns to its equilibrium position without oscillation when it is displaced and released. In this case, omega prime equals to 0. So that's b is greater or equals to 2 times square root of km. The other type of damping is underdamping. This is when the system oscillates with decreasing amplitude. So b is less than 2 times square root of km. So here is a graph of underdamping. There's two cases. One is weak damping, the other one is strong damping. As you can see, amplitude decreases in both cases. With strong damping, the amplitude decreases more rapidly. The period t increases. In this case, t naught is a period with 0 damping. When you have a weak damping force, the weak damping force period is almost the same as no damping. So in damping, energy is decreased. Check your understanding. An airplane is flying in a straight line at a constant altitude. If the wind gust strikes and raises the nose of the airplane, the nose will bob up and down until the airplane eventually returns to its original altitude. These oscillations are undamped, underdamped, critically damped, or overdamped. So we know it's definitely damped because it's bobbing up and down and eventually returns to its original altitude. So it can't be number 1. It cannot be number 3 or number 4 because number 3 and number 4 means no oscillation. So number 2 is a reasonable one. That is the answer. Damped oscillation with periodic driving force. If we apply periodically varying driving force with angular frequency omega d to a damped harmonic oscillator, the motion that results is called a forced oscillation or driven oscillation. So just like the animation shows a monkey is pushing the simple pendulum. So this is a forced vibration. In this oscillation, the frequency of the pendulum is the same as the frequency of the monkeys pushing it. So the frequency is not the natural frequency, but the monkey's frequency. Let's take a look at a resonance. When driving frequency equals to the object's natural frequency, the amplitude increases sharply when there is little damping. This is a case of resonance. So each curve in this diagram, each curve shows the amplitude A for an oscillator subject to a driving force at various angular frequency omega d. Successive curves from blue to gold represent successively greater damping. So as you go down from blue to green, to red to black to gold, the damping is greater and greater. In the horizontal, represent the ratio of driving frequency over natural frequency. When driving frequency equals to natural frequency, when the ratio equals to 1, as you can see, the amplitude increases. A lightly damped oscillator exhibits a sharp resonance peak when the angular frequency of driving frequency is close to omega, the natural angular frequency of an undamped oscillator. Stronger damping reduces and broadens the peak and shifts it to lower frequency. If this condition holds, B is greater or equals to 2 times square root of Km, this is critical damping or overdamping. The peak actually disappears completely. There is no peak at all. So this is driving frequency omega d equals to natural angular frequency at this point. That's when the ratio equals to 1. So the fact that there is amplitude peak at driving frequencies close to the natural frequency of the system is called a resonance. So this is called a resonance, the increasing amplitude. Resonance and its consequences. So all these are examples of resonance. Suppose you are swinging and next to your friend and you're sitting in the same swing, you have the same mass, supposedly. So if you're swing very hard, your friend will swing also with the same frequency as you, even though your friend may not be pumping his or her legs. So this is because your vibration caused your friend's vibration. Your frequency matches your friend's natural frequency, caused the resonance. Another example is the bridge. So if there is a wind that matches bridge's natural frequency, the bridge is going to oscillate. And this is the tuning forks. One tuning fork can cause another tuning fork to vibrate at the same frequency. So building up, this physics is full of examples of resonance, building up the oscillations of a child on a swing by pushing with the frequency matches the swing's natural frequency. Inexpensive loudspeakers often have an annoying boom or buzz when a musical note happens to coincide with the resonant frequency of the speaker cone. Another example is a company of soldiers who actually once destroyed a bridge by marching across it in step, a frequency close to the natural frequency of the bridge. So now when the troops across the bridge, they are told to set steps, not have the same frequency. Another thing, I'm sure everybody have seen this clip, is collapsing of Tacoma Narrows Bridge. And that's also just like this, the wind's frequency matches or very closely matches the bridge's frequency, resulting in its collapse. Okay, last question. When driven at a frequency near its natural frequency, an oscillator with very little damping has a much greater response than the same oscillator with more damping. When driven at a frequency that is much higher or lower than the natural frequency, which oscillator will have a greater response? Let's take a look at this picture. The blue one is a lightly damped oscillator, and the black one is more damped oscillator. As you can see, it doesn't matter whether frequency is high or low. The lightly damped oscillator always have a greater response. So the one with very little damping have a greater response. So that's the answer. That's it for today. Thanks for watching.